This is chapter 26, example 3. And so what we have here is the need to design a counter such that it counts in this sequence. The sequence is kind of special. If you look at it, you can see it's counting up, it hits 7, counts down, hits 0, starts back counting up. The issue is that what we see here, the count is it's either incrementing or decrementing, smells like a counter, and it's going through the sequence of 0 through 7, which certainly feels like a 3-bit counter. This circuit has no other inputs other than a clock, because it's going to be sequential, it's a counter. From that, we have to figure out how to do this. Very first thing we want to do in the circuit is just to draw the black box diagram. The issue on the circuit is it counts up, and then it counts down, and then it counts up, and then it counts down. So the issue is it has to remember the direction it's counting in. So sometimes it's counting up, and after it's done counting up, it counts down. So this feels like it has, if you think about it, it has two physical things that it does. I'm trying not to say states. It either counts up or counts down, but first it counts up, then it counts down, then it counts up. And if you can kind of envision that this is going to be a two-state machine, and the output of that state machine is going to control the direction of the count. This is worth getting into. We think there's a state machine in there, and we know there's a counter in there. So the counter is just going to be a standard counter. We need an RCO on this thing. That's to tell us when it's going to hit its terminal count, and we certainly need control over the count direction, and it's going to be clocked. The issue here is we also need to control this with a state machine. What I'm going to steal on the circuit is this is a control input. That's going to be an output of the state machine. This is a status output. That's going to be an input to the state machine, and the state machine's clocked. While we're at it, might as well put this in here. It's going to be an up-down counter. Up equals 1. Done everything we need to do on this one. As far as the circuit goes, remember I did not connect status and control signals. I will only connect data signals. This is the only data signal. These are the control and status signals. This RCO is connected to that, and it's connected because the names are the same. So the last thing we need to do here is a state machine, and we kind of agreed that it's two states. Count up and count down. What we're going to do here is keep counting up so long as I don't get a ripple carry out. When I get a ripple carry out, I want to go to the down counting state. It's the same thing roughly for this other state, RCO not and RCO. And what we need to do is control the up and the down. So here's the up, it's counting up, and here's the down, counting down. Now, so I think this looks pretty good, looks pretty intuitive, but there's an issue. The problem with the state machine as it is that I've designed it as a more output. The up is a more output. So what's going to happen in this count up state, I'm going to hit 7, the RCO turns on, but the up is still turned on. So the next clock cycle is going to get me to this down state, but it's also going to increment the counter from 7 to 0. And that's not what I want. I want it to, after it hits 7, I want it to decrement down to 6. The state machine as is does not work, so we got to fix this thing, and a couple ways to do it. I think the easiest way is to simply make it into a Mealy machine. So this is going to be up, and this is going to be up not. When it hits that RCO, when it's 7, it's going to count down and transition to this next state. This is the same thing here. This is up, and I think it's going to be the opposite. So it's counting down, and then it's going to count up. This right here is the proper state machine. This is actually a very good problem because it highlights kind of the fact that you have to be very careful with these, and particularly it's always the boundary conditions. You have to put most of your effort into fixing this. Now the boundary conditions are when it's the upper count and the lower count. when it hits 7 and when it hits 0. Keep in mind that this is an up-down counter, so the RCO is dependent upon the count direction. So when it's counting up, the RCO turns on when it's at 7. When it's counting down, the RCO turns on when it's 0, and I've taken advantage of that in this state diagram. I don't need to put a node in there. It's understood. That's how the RCOs work. If it works something different than that, then you'd have to put a node in it. But lastly here, we're going to make a final check on this thing, and it looks pretty good. We have to say what controls this thing, and this is specifically circuit control. And we will call this done.